So let's discuss the relationship between linear and angular kinematics. We have compared linear and angular kinematics before, and this is especially related to rigid body rotating around an axis of rotation. So let's start by drawing a rigid body. Okay, so here I'll have the shape. Okay, here's a rigid body, and it's pinned at this point, which is the axis of rotation. Okay, so it's able to rotate, but only around this axis. And if this is the case, there are some relationships among rotational and translational kinematics. So let's do this one here. We already know that the linear velocity is equal to angular velocity times radius, right? So wherever you point, say this point here, if this shape is rotating this way, so counterclockwise, and there will be a velocity here, and this velocity is related to the angular velocity and also the radius. So as you can imagine, if you trace this line back to the axis of rotation, this point, it does not really move. It could be rotating around itself, but it doesn't have a linear speed. It's not moving anywhere. So having less radius means having less linear speed, or even zero if you have zero radius. So this point halfway only has to trace half the circle. This one has to rotate around. Let me see if I can draw a circle around the axis of rotation. Okay, so not a very good circle, but this tells you that this point on this rigid body rotates around the circle. The point traces a circle, and that half radius. Maybe I can do a little better than that. Just erase this line here. Try to redraw it. Maybe put some reference dots here. Okay. Yeah. So this is half the radius away, so it only has to trace half the radius of the circle. So the linear speed only needs to be half as much, because this circle has half the circumference length, right, compared to this bigger circle. We have discussed this before, so that's not very interesting. What's actually also very interesting is what if this object, this rigid body, is accelerating. So this works whether you see any acceleration or not. But what if there is an angular acceleration? So the object is rotating faster and faster. That means this point here has to complete this circle within shorter and shorter amount of time. So that requires the linear speed to increase, right? So the linear speed needs to increase. That means there needs to be an acceleration along this direction. But we also know that in order to even maintain that linear speed, we need this centripetal acceleration. So now we could have two separate accelerations, right? So now I have duplicated this object, and there's the radius, there's also the velocity, and we anticipate this velocity will increase. So we know that there's going to be an acceleration along this direction. I'll draw it on the outside. So we have an acceleration in this direction in order to increase the velocity, so that this point will cover the circumference at less amount of time. So we call this the tangential acceleration, which is tangent to the circle that this point traces. So this is responsible for increasing the magnitude of the velocity. So this A tan is basically dv over dt. This is just magnitude. So at the same time, we also need this acceleration. This is a centripetal. And in this context, we call this the radial, same as acentripetal, because it points toward the center, right? So this is responsible for changing the direction of the velocity, right? And this acentripetal is responsible for changing the direction, and we know the amount is v squared over r, or you can also express that as omega squared times r, right? And this tangential here, because we have found the relationship between omega, r, and v, right? We have this relationship. We can also have a similar relationship if you just plug this into that formula. So let's see how that works. So d over dt, taking derivative with respect to time, and omega r. Right, that is according to this. So let's have this line here indicating we got it from there. So we know that radius is not changing because this is a rigid body, and if we pick the point, it's just like put a pin on a piece of paper that I cut out in this shape. That pin doesn't change its radius from the axis of rotation, so that this radius is a constant of time. But the angular velocity is not necessarily constant of time, and as a matter of fact, we're trying to increase the angular velocity in some fashion of time. So this is r d omega over dt, and d omega over dt is defined as angular acceleration, so r alpha, right? So we'll have this review. D omega over dt is the alpha, so angular acceleration. Oops. They're trying to get to the dot. That's okay, I'll keep it there. Alright, so this is the angular acceleration. And now we have a relationship between the tangential linear acceleration that is responsible for speeding up the velocity and the angular acceleration. So this makes sense. This point has to accelerate proportional to its radius. So it gets faster and faster, but if you only talk about the halfway point here, it only needs to increase its velocity half as quickly because it's only having half as long of a circumference, right? So if it needs to cover that distance with less time, it just needs proportionally less velocity than covering a larger radius, a larger circumference within that same amount of time. So these two are related. And as we already know that this, now we're defining the centripetal acceleration as a new symbol, a radial. And because of this diagram that I drew here, these two accelerations are perpendicular to each other. They each are responsible for one thing. This increasing the magnitude of the velocity, this changing its direction, the velocity direction, to maintain the circular motion in place. So you can imagine as you travel, this is going to increase. If you have, say, if you speed up from rest, this is going to increase because the velocity magnitude gets bigger and bigger, and this quantity will increase. And that could actually stay the same, maintaining a constant angular acceleration to result in a constant tangential acceleration. So this could be a constant, while that increases with the simplest possible accelerated motion if you rotate something around this axis of rotation, right? So you can combine these two to find the total acceleration. So let me redraw that over here. So the tangential and the radial try to make this a 90-degree angle. I'm not trying to make this horizontal. This is just by chance. So this is the A total. So that this A total is equal to A tangential squared plus A radial squared root.